Okay, so how do we solve a vector addition problem if the vectors we're dealing with are not perpendicular, meaning there's some angle to each other? Well, in order to solve a problem like this, we have a 4-step process. The first process is to break all vectors down into their horizontal and vertical components. So I'll say break vectors down into components. On my diagram on the right, I have two vectors, A and B, that although they look kind of perpendicular, they are not. I'm going to go ahead and break those down into components and show you what the first step might look like. We'll go into more depth on in the next slide. Vector A right here has two components, right? I can draw in the horizontal component. This will be my A sub x, and then I can draw in the vertical component, and that would be my A sub y, right? Those are the individual vectors that make up vector A. I can also break down vector B into two component vectors. This would be the horizontal piece, and that would be the vertical piece, B sub y. And again, I'm just drawing in the legs of the right triangle that vector forms, essentially. So I have these components. What I can do is actually calculate each of those components using trigonometry, and then my second step is to sum all of the horizontal components, and then also sum all vertical components. So I'll do this separately. So essentially we'll take, I'll show this down here, AX plus BX, and we'll take, right, AY plus BY, and that will give me my resultant vector, my RX and my RY. So if I add up all of the horizontal components and all of the vertical components separately, I will get the overall horizontal and vertical component of my resultant vector. What I can then do is use the Pythagorean theorem, good old Pythagorean theorem, once I know these two things, right? So once I have Rx and Ry, I essentially have two legs of a right triangle, and I can use the Pythagorean theorem to solve for the magnitude of R, my resultant vector. Now, that won't give me the direction. In order to solve for the direction, I'll go ahead and actually show what R looks like too on my diagram, just to give you an idea. So R, I'm going to show that in green, would stretch like this, right? And then if I were to think about the legs of this triangle, it would look something like this, right? So it would be like this green, keep going, and then down here. So this would be my Rx and my Ry. It should be interesting to see this Rx, right? You can kind of see it's just the combination of AX and BX if I add them together. Now, because BY right here, BY, because this is pointing down, this is actually going to be negative, and we'll see that when we do the example problem. But so the Ry here is actually the subtraction of AY and BY, or adding an upside down BY. Don't worry about that too much, but just want to point out that that's why Ry is kind of small here, because AY pointing up, BY pointing down, and so it's actually just the difference of those two. But again, don't worry about that for now. This is the fourth step then, is to take this triangle and to solve for this theta value. You would essentially we often use tangent inverse. So that'll be the most common method, tangent inverse, to solve for theta, and then report using compass directions. So making sure that we are aware of what our nearest compass directions are. Okay. So in this case, to solve for that theta, I could do tangent inverse of, that would be opposite, so Ry over adjacent, that would be my Rx. But just as a general trend. And so we're going to do an example problem on the next slide. I'll actually break down these two vectors into their components. I'll add them together, use the Pythagorean theorem to solve for the magnitude of R, and then tangent inverse to solve for the direction of R. Okay, so these are my two vectors. These are the same two vectors from the previous slide. And let's go ahead and give them a magnitude and direction so we can solve. Let's say that vector A represents a displacement of 20 kilometers. And let's say that the direction of A, if I show in the horizontal here, this will be 30 degrees. And we can report that as, right, north of east. If this is my east and this is my north, okay? Then vector b, let's go ahead and give that a magnitude and direction as well. Let's say this is actually 35 kilometers. And the direction here, if I show in my east, and I'll show in the north-south axis as well here. Let's say that this theta right here from east is 45 degrees. So I know I have two vectors, they both have magnitude and direction. I'm going to begin step one by breaking them each into their individual horizontal and vertical components. Okay, so if I go ahead and show this on the left-hand side for vector A, the x component would look something like this, right? I'll show a dot over here. This will be my vector A sub x. And this, if I draw in the vertical component, that would be my A sub y. And I can use trigonometry to solve for A sub x and A sub y, which I'll do now. A sub x, I know, is the adjacent side to the angle that I was given. So that means that cosine of 30 degrees is equal to A sub x over 20 kilometers, right? This will be cosine the adjacent side over the hypotenuse. That means that A sub x is equal to 20 times cosine 30 degrees. Now I can do the same thing for A sub y, noting that this is the opposite side of the angle that I was given. So I will use sine. Sine of 30 degrees will be equal to A sub y over 20, meaning that A sub y will be equal to 20 times sine 30 degrees. Okay, and I can write these in my table now. I'm actually going to leave them as they are until I go to put them into my calculator. So A sub x will be 20 cosine 30, and A sub y is 20 sine 30. Because of rounding error, it's important to either leave these as they are or to round them to maybe 4 or 5 decimals in your work, just to make sure that you're not introducing rounding error as you do your calculation. Now for vector b, I can split this up into components like so. I can go ahead and draw this up here. So this is going to be b sub x, right? The horizontal piece. This will be b sub y here. There we go. Now, I know that b sub x, again, to this angle, b sub x is still at the adjacent side here. So I can once again use cosine. So cosine of 45 degrees would be b sub x over 35. That's my hypotenuse in this case. So b sub x would be 35 times cosine 45 degrees. Now, my b sub y is the opposite side, right? Opposite side, so I can use sine. So sine of 45 degrees would be b sub y over 35, meaning b sub y is going to be 35 times sine 45. Now, this is very important. Stop here. It's important that when we find the components, we also keep track of whether they're pointing in the positive or negative direction. Now, if we define our coordinate axis like so, I'll go ahead and draw this here in green. If up is positive and right is positive, then that means, right, that left and down would both be negative. So please confirm for yourself, right? Vector b sub y is pointing down, right? In order to complete this triangle, I went over to the right, so b sub x is positive, but then I went down with b sub y. So this is actually going to be negative 35 sine 45. So anytime you have a vector pointing to the left or pointing down, anytime you have a component that's left or down, those will both be negative. Now notice for both a sub y and a sub x, this one was pointing to the right and this one was pointing up, so they were both positive, right? Checks out. And b sub x is pointing to the right, so that's positive. B sub y, though, however, in this case, is the only vector in the negative direction, so you do need to keep track of this when you're doing your calculation. Okay, so then I'll go ahead and add these two to the table as well. B sub x is 35 cosine 45 degrees, and b sub y is negative 35 times sine 45. Now the last step is just to add our x components and our y components. And because we've made b sub y negative, we can just add them together and we'll be sure we get the right resultant vector. So adding a sub x and b sub x, for r sub x, I will get 42.069 kilometers. And I'm keeping several decimal places because I'm going to use this again for calculation and I don't want any rounding error. And then if I add my vertical components, so 20 sine 30 minus 35 sine 45 or plus negative 35 times sine 45, I will get negative 14.749 kilometers. Please make sure when you're doing these calculations that your calculator is in degrees mode. You will need to use degrees mode for everything we do in this class up until the end of the year, so please make sure when you're doing these that you set your calculator in the correct mode. Before we move on to the next slide, I'd also like to point out that for vector b, I drew the triangle in with the two components you see here because I was given this angle. But if for some reason you were given this angle instead, say you were given this theta value, you can instead draw by like so and bx like so, right? So again, these vectors, they are able to be translated through space. You don't have to draw them in the order that I showed. They just have to complete this triangle essentially. So I always try to make sure that I draw my components to contain the angle that I'm given. So just be mindful of that as you're solving these problems. There are many different ways to go about solving them. Find the method that works best for you and the problem that you're given. Okay, we're almost there. The last two steps involve drawing out my resultant vector triangle, using Pythagorean theorem to solve for the magnitude, and then tangent inverse to solve for the direction. Now, I've drawn the resultant vector here. I cheated a little bit. I know what it looks like, just as a guide for myself. But when I draw my resultant vector triangle, I always think about, is the x positive or negative? Is the y positive or negative? And then that helps you figure out how to draw your triangle. So because the x is positive, this is going to point in this direction. And because the y component here is negative, I know that's going to point down. And so essentially my triangle is going to look something like this, right? It's going to be this right vector, so this horizontal vector pointing to the right, and then I have a vertical component pointing down. This is my r sub x, and this is my r sub y. So this is 42.069 kilometers. And then I know r sub y is, I'm not going to write the negative here because I already accounted for the negative by showing it pointing down. So that's going to be negative, oh, I just said I wasn't going to do that, 14.4749 kilometers. There you go. Check yourself when you're doing this. Okay, so now I can use Pythagorean theorem to solve, right? If this is r, then I know that r is going to be the square root of r sub x squared plus r sub y squared, right? I get that from the Pythagorean theorem. That means that r is going to be equal to the square root of 42.069 kilometers squared plus 14.749 kilometers squared. If you know how to store variables in your calculator, if you don't, please talk to me. I'd be happy to help you with that. But you can also store these in your calculator to make this a lot simpler. So if I plug these in for my resultant vector, I will get a magnitude of 44.6 kilometers. And I'm okay to round here because I'm not going to use this for any more calculation. Okay, now I'm not done. This is the magnitude, but I also need the direction. So this theta right here will be my direction. And I'll report this if I draw in my reference axis here. If this is north, this is east, south, and west. I'll see here that this is going to be some theta going towards south from east. So this will be south of east, but I don't know what the actual value for theta will be. So I can use my good friend tangent of theta. In this case is r sub y over r sub x, right? The opposite side over the adjacent. So that means that theta will be tangent inverse, or in your calculator it might be arctangent, of 14.749 divided by 42.069. And that will give me a theta value of 19.3 degrees. And again, we said that was going to be south of east. So I would report this as 44.6 kilometers at 19.3 degrees south of east. That would be my resultant displacement from my two displacement vectors. Okay, so I know that was a lot. Please review the videos and begin working on the practice problems on Canvas to make sure that you apply every part of this process. I also have another video recorded where I go through an additional example of adding 3 vectors, in this case 2 vectors at angles and 1 vector that's horizontal, So please watch that video if you would like to see an additional example worked out. This does get easier the more that you do it, and we will be using this throughout the year. So please make sure you feel confident in this, and please come talk to me if you have any questions about this process. Thank you.